Now let us go into the next topic, that is the basic gates. The basic gates are the Nand gate, NOR gate, the inverter, which are used in designing the complex circuits such as SRAM, MUX, analog to digital converters, and various other circuits which will be used in the ICs. First one, coming to the inverter. As we have already studied, the inverter can be made of only N transistor, that becomes NMOS logic. And if we are using NMOS and PMOS, that becomes the CMOS logic. And here what we have is BiCMOS logic, that is, along with the CMOS design, we also have the BJT transistor, which represents the BiCMOS logic. The NMOS transistor, it will have, it can be designed with various aspect ratios. The few of them is discussed here. This is the first case where the pull-up, the aspect ratio of pull-up is, that is L by W, is 8 times that of the pull-down. And because of this, because it is 8, that is the length is 16 and the width is 2 lambda, you get 16 by 2 as A. And from the sheet resistance, we know for an N depletion, N diffusion type, the N type, the sheet resistance value is 10K. Multiplied with 8, you have 80K. And similarly for pull down, it is 2 lambda by 2 lambda 1. 1 into 10K will be 10K. And power dissipation, suppose here V is 5 volt, V square will be 25. When you divide this, see 25 by 90K, 80 plus 10, you get 0.28 milliwatts. Similarly, when we are going for the aspect ratio, that is when you have a length of 8 lambda and width of 2 lambda, then here the length is 4 lambda and the here length is 2 lambda and width is 4 lambda. In that case, what will be the aspect ratio? Here it is going to be 8 by 2, 4 into 10K is 40K. Here this pull down is going to be, it is going to be 2 divided by 4, 0.5 into 10 will give you 5K. Totally again, when we apply phi equal to V equal to 5, that is V square is 25 by 45K, it is 0.56 milliwatts. So we see that as the aspect ratio, that is as the length and width of pull up and pull down varies, the power dissipation will also vary. And similarly, when we are coming for the CMOS inverter design, we have already studied about CMOS inverter, how the length has the length and width of these NMOS or PMOS varies, how the switching characteristics or the transfer characteristics of the inverter varies, as beta P by beta N varies, how the switching characteristics of this CMOS device will vary. And here the aspect ratio, the geometry of PMOS device has to be more than that of NMOS, because the mobility of PMOS device is less compared to NMOS. And to keep the that raise time and fall time delay same, the PMOS aspect ratio or the geometry has to be increased. The width has to be increased to decrease the delay. Next is BiCMOS. BiCMOS circuits are used whenever we have to drive large capacitive loads. Because we know BJT transistor, they have high output current. And because of this, they can drive large capacitive loads and the delay will be less. Next, coming to, this is the basically how a BiCMOS device logic is written. Later on, we'll come back to this again. This is Nand gate. That is, this will be NMOS NAND gate, CMOS NAND gate, and BiCMOS NAND gate. Here, again coming to this NMOS NAND gate, here the NAND gate area will be more than NMOS inverter, because for NMOS NAND gate, the pull down transistors are added in series, but the input, but as the input increases, the length of the pull up should also be adjusted to maintain the same overall ratio. And here, this will be, and moreover, the static dissipation in a NMOS transistor will be more because this is always on. And when A and B are also 1, the entire, all the 3 transistors are on, and you have more static dissipation. Coming to CMOS device, the static dissipation is minimum, ideally speaking, 0. And in CMOS NAND gate, the adjustment in the transistor geometry may be necessary to keep the transfer characteristic symmetrical about the symmetrical about VDD by 2. And the fall time will be more due to the series resistors, because we have the 2 series and gate here. And while discharging, or while fall time means the output has to discharge, it has to go through these 2, and these 2, when the resistance will be more here, so it will affect the fall time of the CMOS NAND gate output. And next, as I said, bi-CMOS device basically used to drive large capacitive loads, and also can be used when you have more fan out, wherein the current has to be more. Next, coming to the here again, you can see that is a minimum aspect ratio. The output has to be, that is here, this output has to be less than, when both of them are on. Even A and B are on, the output goes to 0. And here it has to be less than VT. That is, if VT is around 0.2 VDD, Vout should be less than or at least equal to 0.2 VDD, not more than that. Now, considering that, we know VDD, that is output voltage, Vout will be equal to VDD into the Z value. The Z is nothing but the pull-up aspect ratio here. Z value will give you the aspect ratio. So Z pull down, N into Z pull down divided by N into Z pull down plus Z pull up. So now cancelling VDD on both sides, you have N Z pull down divided by N Z pull down plus pull up will be equal to 0.2. Therefore, this will give you a ratio of N pull down to, that is the AND gate ratio. The pull down to pull up should be around 4:1. The ratio will be 4:1 here. And then next, coming to the NOR gate, the NOR gate will have more area. It will occupy the NMOS NOR gate will occupy more area compared to the NMOS NAND gate. And again, in the it is as fast as corresponding to the inverter, and it is preferred inverter circuit. The CMOS, that is CMOS NOR gate, since P transistors are in series, the resistance will increase, which will affect the raise time. There in a NAND gate, it was affecting the fall time. Here, it will affect the raise time. So overall, the delay will increase, and the transfer characteristics will shift, reducing the noise immunity. Now, when we are comparing the, that is when there is, from some study, I just took the table to give a comparison for NOR and NAND gate. You see, in a NOR gate, the static power dissipation is more, whereas in NAND gate, the static dissipation is less. And this is for a CMOS NAND gate. Ideally speaking, it should be 0, but here it is in terms of picowatt. So it is less here, and in NAND gate, it is even more less. And coming to the raise time and fall time, if you see, comparatively, the NAND gate will have less delay than the NOR gate. Area occupied by this also is less. Here delay is less. This is 10, and whereas 10 nanoseconds, this is 0.125 nanoseconds. So when we compare all this, we see that NAND gate is better compared to the NOR gate because it occupies less area, and the switching characteristics and noise margin of a NAND gate is better than the NOR gate. Next, coming to the different types of inverters. The first inverter would be the resistive load inverter. Resistive load here means in the place of pull-up, a resistance is connected. and it acts as a load here. So it is resistive load inverter. And here it behaves like a depletion type inverter itself. When Vin is 1, this transistor is on and output is 0. When this is 0, output through the resistor will be connected to VDD. But here what that is, here the transistor will have more power dissipation. The power dissipation will be more because we are using a resistance, and this value, that is the noise margin, will also get affected. Next, NMOS inverter. NMOS inverter means the load will be an NMOS device. Here it can be a enhancement NMOS device or depletion type NMOS device. Coming to the first type, that is the enhancement mode NMOS device. Here the load will be of NMOS type, and under this also you have two types, that is saturated NMOS. It is linear enhancement load inverter. Saturated enhancement mode load inverter means here this, when will the device go into saturation? When the that is output voltage is more than the gate voltage. So here we have, this is also connected to VDD, this is also connected. So what will be VGS minus VT? It will be less. This VDS will be more. Output voltage will be, that is, here we have connected the drain to, this drain to VDD. So obviously this device is in saturation. When we look at the transfer characteristics of this, though we have given an input voltage of 10 here, the output doesn't reach 10, nor does it reach 0. See, it is around 3. So we don't get a full output voltage. A full swing is not achieved, and we do not get a full output voltage swing, and it suffers from high power dissipation because saturation current is high, and here also current will flow, and when both the devices are on, the current dissipation will be very, very high. It requires a single voltage supply. That would be a disadvantage, but most of the case you will have only sorry, this is an advantage, but a disadvantage is more because you don't get a proper output and power dissipation is more. Next, coming to the linear enhancement mode inverter. Linear means these VDS should be less than VGS minus VT. When will the device go into linear? That is when VDS is less than VGS minus VT. And here this is VD. And here when we keep this voltage less, that is this voltage, when this voltage is less, this voltage is lesser than, this is more and this is less, then the device is in linear region. In that case, let us look at the graph here. The graph also here, compared to your enhancement saturated mode, this is comparatively on the lower end, the output voltage it reaches 0, but it is not reaching the full VDD value. It is somewhere around 5 volts. The VDD given, it doesn't have the proper full. It operates in linear region, and here it reaches this VGS voltage. It is able to reach the VGS voltage 5 volts. VOH is equal to VDD. Compared to this, it has a better noise margin. It has a better noise margin. But here, this transistors, these inverters are not used because power dissipation, even in this case, the power dissipation will be very high. To overcome this, that is large power dissipation, and depletion type inverters were introduced. And in depletion type inverter, here the gate of this is connected to the source of the device. Again, when we check the transfer characteristics, the input given here is 12 volt. In the other case, it was 10. The output, you see, it is almost reaching 12. And whereas you get that is when Vin is 0, output VOH is better, but your lower voltage value, that is VOL value, is not good. It is not reaching 0, whereas it stops at around 4 volt. So VOL value is not that is lower end voltage is not that good. and it has a static power dissipation will be high. Here, when that is when this input is 0, 1, both the transistors are on, and you will have static power dissipation. And next is CMOS inverter. CMOS inverter, as we have discussed already, that is, it has full, that is, see, in the input voltage was, if we are given input voltage of 10, we get, that is, sorry, that the VDD is 10 volt, from 10 to 0. That is full swing voltage we get, and the power dissipation is very less. Next is pseudo NMOS inverter. Pseudo NMOS inverter means that is a PMOS. We have a PMOS device. A PMOS transistor will be connected to ground, and it will act as a pseudo NMOS inverter. If you look at this comparison table here, when we are looking, it has a poor noise margin. That is, this has, see, all these cases the power dissipation is high. Only CMOS inverter has a lower power dissipation. And here, there has a, as we were discussing, most of the cases on the lower end, it doesn't have a good output voltage. See, VOL value here, VI, that is your this value, that is, it has a poor noise margin for the lower side, and enhancement poor for both low and high. It is not good either on the higher side nor on the lower side. And here even this has a poor for the lower side. Lower side, the output voltage doesn't reach 0. And VIO and VIH, that is input, that is your lower input voltage and higher input voltage. The noise margin, if you see, it is weak, poor for the lower voltages. It is poor for the lower voltages, whereas here it is poor for both higher and the lower voltage. So comparing all this, we finally come to a conclusion that CMOS inverters, they have a better noise margin, they get a full output swing, and the power dissipation is less. Next, coming to the ratioed logic, we have ratioed logic here means that is all what we have discussed till now. Apart from CMOS device, the other, all the other, this is the pseudo NMOS. As I was telling you, pseudo NMOS means you have a pull down and you have a P transistor, and the gate of the P transistor is connected to ground. It acts as a pseudo NMOS. Pseudo NMOS means it is actually a P transistor which behaves as a NMOS depletion type, because this is always on. So this also is always on and it behaves or acts as a NMOS. So it is called pseudo NMOS device. Then ratioed logic. What is ratioed logic is here. See, when this transistor, now when say for example in this case, here when we have depletion type, now when Vin is 1, this transistor is on and this transistor is also on. Now output has to go to 0, and this output has to go to 0 means the aspect ratio of this transistor should dominate the aspect ratio of the pull-up transistor. The aspect ratio of the pull down should be more dominant than the aspect ratio of the pull up transistor. So it is called a ratioed logic. Ratioed logic is when in these cases, we will have in these cases when the pull up is always on, and when pull down is also on, the output has to go to 0. But there will be a fight between pull up and pull down. So this pull down has to be more stronger than the pull up, and its ratio or the dimensions or the aspect ratio, a W by L ratio of this should dominate that of the pull up transistor, and it has to pull down the output voltage to ground. So that is ratioed logic, whereas CMOS is a ratioless logic, because in ratioless logic, when pull down transistor is on, pull up is not on. So there is no fight between pull up and pull down. Either pull up is on or pull down is on. You need not match the ratio, or you need not worry about the ratio, whereas in ratioed logic the pull down should be more dominant to bring the output voltage to 0. So that is ratioed logic. Next, coming to static and dynamic CMOS logic. Static means it doesn't have a clock. Whereas dynamic logic, see, this is static, where it is just dependent on the input. Whereas dynamic logic means you also have a clock along with the input. So that is static and dynamic logic. Along with the circuit, you should also have a clock input. So that will be dynamic logic. From next class, we will see what are the different dynamic logics.